We'd like to show you how to do a one-sample t-test in SPSS. Now online, these notes detail an example found in Howell's text in 2002, where the dependent variable is a psychomotor development index, or PDI, taken from the Bayley scales of infant development. So if you scroll down these notes, you'll find details on running a t-test on that data, including some descriptives here, box plot. Now we get down to the actual t-test computations, including how the t-test was calculated here. So these notes are very useful for that purpose. For our purposes, we're going to go right to the data set and show you how to actually run this in SPSS. So here I've entered my PDI variable. There are 56 cases total. I've entered all the data. First infant got 96, the next one got 125, 89, and so on. Now remember the purpose of the one sample t-test. For this example, we're going to adapt this from Howell. I'm going to change the example a little bit. But assume that in the population, the average PDI is equal to 100. Now, that's going to be our null hypothesis. For this particular sample of 56 infants, imagine that we gave them some kind of developmental task. So we gave them some kind of training, and we think that that training is going to boost their PDI scores. So the question we're asking is, do we have evidence to suggest that this particular sample of 56 observations of children was not sampled from a population such that the mean is equal to 100? Okay. Again, do we have evidence to suggest that this particular sample was not sampled from a population such that the mean is equal to 100? That is our null hypothesis. And if you're unclear about that, make sure you check out the notes on the page, read through them, and you'll get used to how to coin that null hypothesis in the one sample t-test context. Before actually running the one sample t-test, I'd like to request some descriptives here. So I'm going to go to Analyze, go to Descriptive Statistics. There I've entered my PDI variable. I'm going to click OK. And here I get a few descriptives. There's PDI, n equals 56. There's my minimum, there's my maximum score in the data. I see that the sample mean is equal to 104.1250. Now remember, this is the sample mean. It is not a population mean. So I would expect this sample mean to deviate from my null hypothesis mean of 100. But the question we ask in a statistical context is, does this sample mean deviate enough from the population mean that I can conclude that the actual population parameter is different from 100? So remember, when you look at the sample mean, this sample mean is not evidence by itself to reject your null hypothesis. 104 could be a deviation simply due to sampling error or chance. We need to do a statistical significance test to gain inferential support against our null hypothesis. There's our standard deviation as well in the data. I'm also going to request a stem and leaf plot. I'd like to take a look at the distribution. So I'm going to go back to Analyze, and I'm going to go to the Explore function. Click on there. Here I've entered the PDI variable in my dependent list. And I just click on that. It offers me a few more descriptives, the median, the variance, all useful information. But for now we want to just look at the stem and leaf plot. There's the stem and leaf plot for the data. I can see that I have a single score of 83. I have a couple 86s, some 89s, etc. The reason why I'm looking at this plot is to just get a sense of the distribution. So by no means is the distribution perfectly normally distributed, but what I'm looking for are potential problems with the distribution, potential serious problems that would prevent me from carrying on with the significance test. For instance, imagine that instead of having 183, I had, say, like 20 or 30 83s. And then I had about 20 or 30 84s. And then the rest of the scores, I had, say, like 192, 193, 1 at 100, 1 at 101, very, very small values. I would have a grossly skewed distribution, almost to the point where even running any kind of inferential test on this distribution would not make much sense because I wouldn't even have much variability. So one thing you're looking at when you're looking at distributions is to make sure that it's reasonably well behaved. Because if it isn't, then conducting your significance test, though computer software will do it, it'll potentially be very misleading because it's doing it on a distribution that is extremely bad, that has extremely bad form and shape. If you have moderate skewness, it's generally no problem for the one sample t-test. So even if this distribution was a little bit more skewed in either direction, it wouldn't really be a cause for concern. Also, I could look at this stem and leaf plot to have a quick look to see if maybe I have any extreme scores that I may be concerned about. They'd be listed on top here or on the bottom. And I have no evidence of extreme scores or outliers in this distribution that I would have to check to make sure they weren't recording errors and things like that. So everything looks pretty good for this distribution. I have no reason to not do the t-test. Remember, the explore function also gives you a box plot, and that's a useful device too for having a quick glance to see if you have any potential outliers. The SPSS would put little stars here at the bottom or at the top to indicate outliers, and everything looks pretty good for this data. So we can continue on with the one sample t-test. To conduct the test, I go to Analyze, go to Compare Means, and I go to one sample t-test. Click on there. I've entered my test variable already, so this test variable is actually over here, and I just moved it over right here, test variable. Right here, very, very important, is the test value. Now this value is the value under your null hypothesis. So in our case, our null hypothesis is that the mean is equal to 100. That's why I've entered 100 there. If my null hypothesis were that the mean is equal to, say, 90, then I would put that in there. Now when you enter this value, remember that this is not an arbitrary decision you're making as to what number should you put in there, or putting in a number there until the computer gives you something that you can work with. If you're not sure what to enter for this value at this point in running the t-test, then you need to go back and revise what your null hypothesis even is. So this is directly born out of your substantive reasoning, out of your research question. So for me, setting it at 100, we had said at the beginning of the example that our null hypothesis was going to be that the mean equals 100, so I know exactly what to put here. But if you're not sure what to put for your research question, I suggest you stop the t-test procedure and you go back and you work on your null hypothesis again to make sure that you have that correct. Click on Options here. By default, I'm going to get the 95% confidence interval. We'll interpret that in a moment when we look at the output. Missing values, I won't talk about this much right now, but you can make sure this first button is clicked, Exclude Cases Analysis by Analysis, and that'll be fine. We're only doing one analysis, so it will not be a problem for us, and this option is perfectly fine. When you have different data situations, there will be a difference between these two that you want to consider, but for now, we're okay. I'll click on Continue, and I'm ready to run the t-test. So there's my output. Remember that you can have SPSS produce the syntax for you. This is what these are the commands that SPSS actually ran by us doing it through Windows. It computed it through syntax. Remember, how is this useful? Well, maybe you want to alter the t-test procedure a little bit or include some details that aren't easily done through Windows. Well, this is the syntax by which you can start by. Here's the actual t-test. There's my PDI variable. My n equals 56, so my sample size is correct. Always check to make sure that your computer output is producing correct figures, to make sure that nothing is being computed wrong, or that it is doing it on the correct column of data. All of this is very important, because if ever this said for some reason 40 or something like that, then you know there's a problem right off the bat, and it makes the interpretation of everything else in your output completely meaningless. There's my sample mean of 104.1250, standard deviation, and there's the standard error of the mean. Remember, for the one sample t-test, this standard error of the mean is going to be used in the computation of the one sample t-test. And going through the notes on the web page will detail where this is used and how it's used. One sample t-test, PDI, there's my t-statistic. Now remember that under the null hypothesis, what would expect t to be? Well, under the null hypothesis, where there is no difference, we would expect this to equal 0. So under the null, where the mean is actually equal to 100, and it does not deviate from 100, this t-statistic would be equal to 0. So we see right away that it's not equal to 0. This lies off into the right tail of the distribution. And the question for us, in a statistical sense, is to ask, does this lie far enough into the distribution that we are ready to reject the null hypothesis? So what's the probability of obtaining a statistic like this, or more extreme, under the null hypothesis? And that's why we're going to look at our p-value in a moment. Our degrees of freedom are equal to 55. Remember, for the one sample t-test, the degrees of freedom are equal to n minus 1. So here I have the sample size of 56, subtract 1, I get the degrees of freedom of 55. And recall as well that these degrees of freedom are important because it tells the software or anyone conducting the t-test which t-distribution to look at to evaluate the resulting t-statistic. So taking a statistics class, when you have to turn to the back of the book to look these things up in a table, this degrees of freedom is very, very important, so you know which line to look at for those critical values. Using software, it's relatively easy because it just prints out the p-value and you don't have to look it up. But otherwise, you would need these degrees of freedom if you were doing this manually. There's our p-value. Okay, significance two-tailed. Now we're doing a two-tailed test because we want to detect deviations on either side of the null hypothesis. Remember, our null hypothesis is that the mean is equal to 100. I'm interested in rejecting the null hypothesis if I have evidence of deviation above or below the mean. Even though we expected our mean to be above 100, I would still be interested in deviations below 100. I would still want to reject the null hypothesis. And that's why we're doing a two-tailed test. Almost in all research situations, a two-tailed test will be performed. It's usually much better to do a two-tailed test than a one-tailed test. My p-value is equal to 0.017. I hadn't mentioned this from the beginning, but I'm going to use a conventional significance level of 0.05 for this example. Why did I choose 0.05? Just for lack of reason for choosing any other value. Remember though that when you choose a significance level, you should have some kind of research rationale for why you're doing so. And that usually amounts to balancing those types of errors that you wish to minimize. So choosing an automatic value of 0.05 all the time is really considered to be bad practice. You want to be able to justify why you're using 0.05, why you're using 0.01, or what have you. For our example, we'll use 0.05 just for convenience. We can see that the p-value is less than 0.05. 0.017 is less than 0.05. And therefore, we have evidence to reject the null hypothesis. Remember, what does this p-value actually literally mean? Well, it asks the question, what's the probability of observing a statistic like this, or more extreme, under the null hypothesis? Well, that probability is getting to be rather small. Therefore, we can reject the null hypothesis. And substantively, what does that mean? That suggests that this sample that we have of 56, on which we've calculated the sample mean of 104, we have evidence to suggest that this sample was not drawn from a population such that the mean PDI is equal to 100. Okay, very, very important interpretation. The rejection of the null hypothesis is evidence that this sample was likely not drawn from a population such that the mean PDI is equal to 100. Which, remember, substantively was our point in doing the t-test in the first place. We wanted to see if our treatment or our program boosted the performance on the PDI. And the rejection of the null hypothesis suggests that maybe we are onto something. Also, you'll see up here the test value is equal to 100. Remember, we entered 100 as our test value. Again, always good to check to make sure that SPSS is printing out the correct value here. If this value were equal to, say, 90 or 80 or some other value for some reason, then all of this is meaningless. So it's always good to double check that. One more thing to interpret is the confidence interval here. The mean difference is equal to 4.125. This mean difference is the difference between the population mean of 100 and the sample mean here of 104. Now we ask the question, what would we expect the mean difference to be under the null hypothesis? Well, if the null hypothesis were so-called true, then we would expect this mean difference to equal what? To equal 0. However, the mean difference is not equal to 0. It's equal to 4.125. So let's see how we can use this idea of the mean difference in the computation of the confidence interval here. The confidence interval is going to give us a lower bound and an upper bound. Lower bound is equal to 0.7549 and the upper bound is equal to 7.4951. There are two ways you can use this confidence interval. One way to use it is in a test of the null hypothesis. Now, because we expected the mean difference to equal 0 under the null hypothesis, we can look at this confidence interval and ask this simple question. Where does 0 fall relative to this interval? Well, 0 certainly does not fall anywhere between the interval. 0 does not fall between 0.7549 and 7.4951. 0 falls over here somewhere. Okay. So because 0 falls outside of the interval, that gives us evidence to reject the null hypothesis at the 0.05 level of significance. Because it's a 95% confidence interval, this means we're testing the null at 0.05. Again, let me repeat that. Because 0 falls outside of this interval, we have evidence to reject the null hypothesis. Now, this is the same conclusion we drew by interpreting the p-value here. So what I'm showing you is just another way of using this confidence interval to test that null hypothesis, and that indeed is another way of testing it. The conclusion that you draw here regarding the null hypothesis will agree with the conclusion of the p-value. A second way of using the confidence interval is to recall the correct interpretation of a confidence interval. Okay, here's our interval, and what this means is that in 95% of samples drawn from this population, this interval will capture the true population mean. Okay. Again, in 95% of samples drawn from this population, this interval will capture the true population mean. In 5% of them, it won't. Now, I want to point out something very important here, because oftentimes confidence intervals are misunderstood, that we somehow think that the population parameter is the random component. But that's not true. The sample is the random component. So I explain this in other places on the web page, but imagine having the true difference as a fixed parameter. Well, it exists somewhere in parameter space. If I take this interval and I literally throw it at the population parameter, so imagine it almost like it's been described as almost like a horseshoe ring. Okay, you're going to throw the horseshoe at the population parameter. Well, the confidence interval tells you that in 95% of samples on which you compute this interval, it will capture the true population parameter. The true population parameter will fall between these limits. And in 5%, it won't. So that's a very useful thing to know to give you an idea of how precise you're estimating that difference. Okay. So So two ways you can use a confidence interval, and again, if that's a little bit unclear, take a look at the notes online where we interpret the confidence interval, and hopefully that will become clear. So we've shown you how to conduct a one-sample t-test in SPSS and how to interpret this test.